Picture the state of AI video not long ago. You typed in a sentence, waited, and got back 3 seconds of nightmare. Faces melted into each other. Hands sprouted extra fingers, then lost them. A person walking would slide across the ground like a ghost, their legs swapping places mid-step. The most famous example, an AI clip of a celebrity eating a bowl of spaghetti, went viral precisely because it was so grotesque. The pasta fused with his face. It was funny, and it was reassuring because it told everyone watching that real video was safe. Machines clearly could not fake it. Then, in a span of roughly 18 months, that reassurance evaporated. The same kind of text prompt now returns clips that can stop you cold. A cafe in the rain, a specific kind of light, a person who holds together from the first frame to the last. Not perfect, but good enough that you have to look twice, and sometimes good enough that you cannot tell at all. Nothing about human perception changed in those 18 months. The machines did. This video is about how and about what is actually happening inside that jump, because the leap was not magic. It was a handful of very specific engineering problems finally getting solved. Start with the thing AI already did well before any of this. Still images. By 2023, image generators could produce a single photorealistic picture from a text prompt. The method underneath is called diffusion, and it is worth understanding in one sentence because video is built on top of it. A diffusion model learns to take an image that is pure random noise, like TV static, and clean it up step by step until a coherent picture appears, guided by your words. Noise in, image out, one careful step at a time. That part was largely a solved problem. So here is the obvious idea, and here is why it failed. A video is just a stack of still images, 24 or 30 of them per second. If a model can make one convincing frame, why not make it make 30 and play them in a row? People tried exactly that. The result was the melting nightmare. And the reason it failed points straight at the one problem that defined this whole era. The problem was time. When you generate each frame on its own, the model has no memory of the frame before it. Frame 1 gives your subject a blue jacket. Frame 2, generated fresh, makes it slightly green. Frame 3 shifts the color. Frame 4 moves the face. Play them back and everything shimmers and crawls, because nothing is holding the world steady from one instant to the next. Making a good frame was solved. Making the next frame agree with the last one was not. Engineers have a word for what was missing. Temporal consistency. Consistency across time. Think about what your own eyes expect. When a ball rolls across a table, you expect it to keep being the same ball, the same size and color, moving in a smooth line, obeying gravity. That expectation is enormous and mostly unconscious. A model that generates frames independently knows none of it. It has to be taught, somehow, that the world has objects, that objects persist, and that motion is continuous rather than a fresh roll of the dice 30 times a second. Teaching a machine that turned out to be the central task, and solving it is most of the story of the last 18 months. The first big fix was to stop treating a video as a pile of separate pictures and start treating time as a genuine dimension of the thing being generated. Instead of denoising each frame alone, the newer models denoise the whole clip at once, as a single block that has width, height, and duration. The model is now allowed and required to look across frames while it works, so a decision it makes about frame 1 is felt all the way through frame 90. The jacket stays blue because the model is building one coherent object that extends through time, not 30 guesses that happen to be adjacent. To make that tractable, the leading systems chop a video into small chunks that span both space and time, little cubes of a few pixels across and a few frames deep. The model learns the relationships between all those cubes, how a patch here connects to a patch a moment later. This is the same core trick, the transformer that made large language models work, now pointed at video. And it matters for a blunt reason. This design scales. Feed it more data and more computing power and it reliably gets better, which is exactly the property that turns a research demo into a fast-moving arms race. Which brings us to the second fix, data and a specific kind of it. To learn how the world moves, A model needs to watch an astonishing amount of video, and crucially, it needs each clip paired with a good description of what happens in it. Early on, the captions attached to internet video were garbage, a file name, and a stray tag. A big, quiet part of the recent progress was labeling, using other AI systems to watch millions of clips and write detailed descriptions of the action, the camera move, the lighting. Better descriptions during training mean the model actually connects your words to the right motion when you ask. A lot of the leap people credit to raw genius was really this unglamorous cleanup of the training material. The third fix was about cost, and without it none of this would be usable. Generating raw video pixel by pixel is punishingly expensive. A few seconds of high-resolution footage is a mountain of numbers. So modern systems first squeeze the video down into a compact mathematical summary, generate inside that compressed space where the work is far cheaper, and only expand back out to full pixels at the very end. It is the difference between sculpting a small maquette and carving the full statue from the start. This compression is a big reason clips got longer and sharper at the same time, rather than one at the expense of the other. Stack those three changes together and you get the jump you have been seeing. Time treated as a real dimension so the world stops shimmering. Transformer architecture that scales with data and compute so throwing resources at it actually pays off. Compression that makes long, sharp clips affordable. Add better labeled training footage on top, and the melting nightmare becomes a stable cafe in the rain. No single breakthrough did it. It was several known ideas maturing at once and reinforcing each other. But hold the hype because this is the machine layer, and the failures are as revealing as the wins. These models still do not understand physics. They have watched enough footage to imitate how things usually move, but they have no built-in rule that says objects cannot pass through each other or that water flows downhill. So they break in tellingly specific ways. Poured liquid behaves wrong. A cut object is whole again a second later. Reflections do not match what is in front of the mirror. And the classic tells persist. Hands still because fingers do a huge amount of fast, fine, overlapping motion. Text on a sign will often flicker into gibberish because the model is imitating the look of letters, not spelling. Object permanence over longer clips remains shaky. Something that leaves the frame may come back changed, or not come back at all. The world these models generate looks right moment to moment and quietly stops making sense if you hold it long enough. They are imitating the appearance of reality, not modeling how reality works. So why should you care beyond the novelty? Because the reassuring assumption that real footage is self-evidently real is the thing that just broke. For a century, video was near the top of our trust hierarchy. Seeing was believing. The technical story you just walked through is also the story of that assumption quietly expiring. The useful response is not panic and not denial. It is understanding the seams. Check the hands, the text, the reflections, the physics of poured and cut and drop things, and the moments a clip has to remember something for more than a few seconds. Those are exactly the places the machine is still guessing. The short version, AI video did not get good by magic. It got good by solving one hard problem, keeping the world consistent across time, using 3 specific fixes, generating a clip as one block instead of separate frames, borrowing the transformer design that scales, and compressing the video so long and sharp became affordable at once. What is left broken, physics, hands, text, memory, is left broken for equally specific reasons, and those reasons are your best guide to spotting a fake. Next time, we are going all the way down to the chip this entire boom runs on, what a GPU actually does that your laptop cannot, and why one company ended up owning the whole thing. Subscribe, and we will keep